and I have it due on Sunday, okay? We can see, it's due this Sunday, okay? And let's see, on this, I can't tell. It might be a little bit longer than homework number 1. I'm not sure. I reduced the parts on the questions, but it's got more questions on it, so I'm not quite sure. And part of that is thinking that because we lost a week because of the ice storm, that there might be fewer homeworks in total, so I should add an extra question or so to each one of them as we go. And so that's there. It does have one MATLAB question on it, okay? And so is that a hand? Or no? Okay. Oh, no worries. It has one MATLAB question. I didn't count it too many points because it's our first one. But I wanted to get into MATLAB and talk a little bit about it. And let me maybe qualify that by saying it's a problem that requires software. And I have provided code for it to be done in MATLAB. Truth of the matter is, I don't really care what software you use. If you can recognize it and do it in Python, because I don't know what your software experiences are at this point. Please.
Yeah, I was going to ask about that. You said MATLAB or its alternatives. So
this can readily be done in Python. In fact, I've had several people tell me that code in Python and code in MATLAB are actually quite similar. It can be done in R, or RStudio or anything like that if anybody wants. I mean, for that matter, well, not really. I want to say it could even be done in Excel, okay? Truth of the matter, I don't know if Excel is a good option, because on it, where I'm asking you to do a simulation and I'm suggesting 1 million trials, okay? And MATLAB is just amazing. Oh my goodness. MATLAB, you want 1 million trials, snap your finger and it's done, Excel, you want to randomly generate 5,000 values, you might as well go get lunch, And so it might not be practical in that, but I'm saying I'm open to whatever you want, okay? And so it has one software, is that how you spell software? MATLAB question, right? And as I said kind of at the start of the course, code is provided. As I said, the goal here is to use a software, use an ability to use simulation to try to see properties, probabilistic properties. It's less a coding class, it's not that. So I'm always going to be providing you with the code. The end result is kind of seeing some observations. And so simulation, and I've, like I said, 1 million trials. And so what's the deal? The deal is essentially this, where that's right here. The law of large numbers. Right? Suppose we have an experiment. Results in either event A or not A. Okay? And we're gonna repeat, and the experiment is to be repeated. The experiment is repeated, okay? And the trials are independent. Okay? And so, by the way, independence is our topic of the day. So after we do this a little bit, we're going to talk about what I mean by independence. What it means essentially is the results of the second trial aren't affected by the first trial or any other trial, right? Right? Well, each trial, you know, think about it like we're interested, we have a coin, we're interested in the probability it's going to land on heads, right? So we're thinking, well, let's just start tossing the coin, right? Right? Well, if you toss the coin 3 times and count how many times it lands on heads, you can calculate the proportion, right? Well, that proportion isn't going to be 0.5, right? Right? Please.
In the event, just a question about a scenario for the law of large numbers, are A and not A equally likely?
No.
Okay.
No, not at all. Not at all. And so the trials are repeated, the trials are independent, okay? And so if you have n trials, x of which result in A, okay, then the proportion of A's, relative frequency it's often called, of A is simply x over n. Okay? Okay? Right? For instance, if you toss a coin 10 times and it lands on heads 7 times, 7 of those 10, then the relative frequency is 0.7. Okay? Okay? What the law of large numbers tells us is that this relative frequency, x over n, converges as n goes to infinity to the true probability of A. Okay? Okay? And so, with a lot of things where, and not only is this true for a single event like A and not A, but it's true for a collection of events like whole distributions, right? Right? That repeated sampling, right, converges to the true distribution, converges to the true probability. And so oftentimes you don't know, but you're interested in what the true probability of something is, right? And so simulation, where you're modeling it using a software that can generate large numbers of things, is a reliable way to get a picture of what that true probability or indeed a true distribution might actually look like. Okay? Relevant for us because you know, so for instance, you designed a circuit and you want to test its reliability, right? You want to know the probability if you switch it on that it's going to work, right? Well, there might not be a mathematical way to deduce that, right? So how can we do it? We can simulate it. It's called Monte Carlo simulation, right? But that's just a catchword for multiple independent trials, right? And using this convergence. And so, you know, indeed, simulation becomes a vital tool in terms of things like reliability of designs and things like that, you know? And so, and you'll hear me say this times again, you know? If you design something, right? Something with interwoven parts and whatever it might be it a circuit, or when I was working in an engineering group, I was in a mechanical engineering group and we were making liquid chromatography things, you know, first off, anything you design, you want to physically build it, right? You want to make sure it works, right? When you physically build it, please.
In probability, do we have a ceiling for what we consider a sufficient number of trials for N?
No, you have a mathematical
Okay.
convergence, and it might very well depend on what the value, you know, some things you can get away with smaller samples, some take a little bit more, you know. Yeah. Now, when you're thinking about it, when you design something, there's a couple things to bear in mind. You know, one is like there's no substitute for actually physically getting your hands dirty and building it, make sure it fits together, make sure it works. But the thing is even if you're physically building something and trying it, at most, how many trials can you have, you know? And, you know, it's probably a fairly small finite number, okay? And so, but the thing is take, for instance, a circuit you've designed. What is it that's gonna make your circuit blow up? You know? If all the components are to specification, then it's probably gonna work. I mean, you're all good engineers. You know how to design things, right? Right?
Yeah.
And yeah. And so, but what is it that's gonna make your thing blow up? You know, it's gonna be the extreme outliers, right? You build something and you're saying it's got a resistor of 20 ohms in it, and all of a sudden, unbeknownst to you, you pull one out of the box and it's mislabeled and it's 40 ohms. Right? I don't know. It's those kinds of things. It's those kind of very rare and unusual events that are gonna cause it to fail. It's not gonna, and you're not gonna detect that if you try it 5 or 10 times, right? You will probably detect it if you try it 1,000,000 times or 5,000,000 times, because eventually in all those simulations, those extreme things are going to occur somewhere along the way, you know? And so while I say there's no substitute to actually physically building it and testing it and making sure all the parts fit and all this and that doesn't really test it for the extreme diverse world we live in. And that's where simulation and Monte Carlo simulation comes in, right? Because eventually, if you try it enough times, you know, then eventually those anomalies start to appear, you know? And it's not like, you know, when you're thinking about a design, you're not really interested in the 99.9 times it works. You're interested in that 0.1% of the time when it fails. You know what I mean? And so, hence, you know, Donald Duncan and people in EE value this simulation, okay? And the underlying piece behind this simulation, any of these simulations, is that when you have independent and identical, I should use the word identical trials, right? Trials are independent and identical. Right? You don't want to change your parameters like midway through your experiment, okay? Then through repeated trials, the relative frequency or the sampling distribution converges to the true distribution, converges to a true probability. And that's the essence of what we're trying to do here, you know? And so, let me see, I'm going to embarrass myself. I'm going to get into MATLAB. Let's just talk about it. How many of us have been there before? Okay, see, that percentage gets smaller every time I teach this class. I'm told, by the way, I know what really happens around here. Okay, I'm told by faculty that everyone gets exposed to MATLAB in their 200 level courses, and so. I know, I heard that, I saw the heads shake. Yeah, And so I want to qualify that by saying, you know, I do realize that. We all come from varying backgrounds. That's why I'm always going to provide the code. It's not like I'm testing on your ability to code. It's, okay. So I've logged in. I'm going to log into MATLAB. Let me see what I can do here. PC. Oops. There we go. Oops. Okay. And there's MATLAB on here. I don't know if it's the same version you guys have. Okay. It takes quite a little while to load. And so one thing to note about MATLAB is it's based on vectors and matrices, okay? And I believe that in that lies its power. Let's see. Come on. Okay. And here is the command window. We'll enter a couple commands here. A couple things that you might want to know, okay? And by the way, on the assignment, I'm asking us to provide a couple graphs, okay? And also provide the code, and quite frankly, you can copy the code, copy the images, and paste them into a Word document and be part of your homework submission. That's absolutely fine with me. The only thing for quality control is I ask everybody to make sure that their name is in the first line of that code, okay, as if that does anything. But the first thing is the, what is that symbol called? What is that? Oh, that parenthesis symbol. No. Yeah. Percentage. Is that percentages? Yeah. Anyways. Okay. Everything to the right of that is considered text. Okay. It's not code. Okay. Every good programmer knows you want to add comments so that you can troubleshoot down the road. Okay. So anything, if you ever want to add a comment in there, use that percent sign, and any text after this is comments, not code. Okay. Another thing I'll mention here, since I can, is that MATLAB is case sensitive. Okay. By the way, if you make a mistake and you want to go up and fix it, you can use the arrow buttons to go up or down, okay, to edit code, okay. Another important command is, and I'll put it again in the comment, otherwise it's going to give me some sort of error message. The symbol, let's see, the symbol, which one is it? It's the, what's that thing called? A semicolon? Is that thing called, is that a semicolon? I don't know what any of those things are. Okay, the semicolon placed at the end of a command line suppresses the output. Okay? Okay? Added at the end of a line of code suppresses the output. Okay? By the way, I don't know if I spelled suppresses right. That's a little button you want to remember, because remember, I'm going to ask you to do a simulation of 1,000,000, right? If you don't put that at the end of that code, then it's going to list out all 1,000,000 values, right? Right? Okay. You'll do it once, and then you'll realize, oh, that's a good thing to remember. Okay. Okay. And so, what can we do here? Okay. So, for instance, let's see, let's let capital N be equal to 10. Okay? You notice I won't use that symbol this time, and it reports N is equal to 10. Okay? So let's say N is equal to 10 and suppress the output. See what I mean? So it just held that back. Okay? And now let's let X, and do I want to be capital? As long as I remember, X equals rand 1 n. Okay? This, yeah, maybe I should. Maybe I won't. Okay? I'll just put a comment there. What this does is this creates a vector of length n. Okay, in this case 10. Okay, it creates a vector of length n. Okay, and with entries being random numbers between 0 and 1. Okay? So that RAND, what it's doing is randomly generating from what's known as a uniform 0-1 distribution. So it's randomly generating values between 0 and 1. This is going to generate 10 of them. Okay? As I said, populating a vector. Okay? If you want to know, yeah, please.
I'm just curious, it looks like when you declared n, you just said 10, and that was that, and it seems like it saved it as just like the integer value 10.
Mhm.
What did you do different to your variable assignment of x that warrants generating a vector versus just generating a single integer?
So I'm gonna, the RAND is saying I'm gonna randomly generate from the 0, 1. This here says I'm gonna populate a matrix with 1 row and n columns.
Oh, okay.
Okay? Okay? Right? And in fact, let's see, I didn't put the suppression in there, and so those are the n values. Right? Right? And so for instance, and so let's take that a step further. Let's let n be equal to 10. Let me add one other thing. X is, I'm gonna recopy over this. Okay. 1 comma n, close that, is less than 0.5. Okay. Now what this is doing, this is creating a logical statement. Okay. And so in this case, what it's doing is randomly generating 10 values, the same as before, but then that less than 0.5 is adding a logical statement. If the value is what? Less than 0.5, then it's going to assign a 1. If the value is greater than 0.5, it's going to assign a 0. Okay? Right? And good. And then, so maybe I'll suppress that. Okay? And then let's see, and so don't forget, well, maybe I will add this comment in here just so, I should try to save this after everything's said and done. I don't know. This generates one vector of zeros and ones, okay? 1 if the random value is less than 0.5 and 0 otherwise. Okay? Right. And if I go and look at those, well, I suppressed that one, okay? Okay? Right? And now since this is coded 0 if it's greater than 0.5 and 1 if it's less than 0.5, then the sum of those x values would be the number of times it was greater than 0.5, less than 0.5, am I right? Right, please.
So this has been something in previous coding classes, we've encountered issues with. For the sake of our simulations, is the rand function sufficiently random enough for us?
It's sufficiently random for us. I don't know how it actually works.
Okay.
And there's a way that you can add a seed to it too, so that you could reproduce it. Yeah, that's always a good question. How is it actually doing that simulation? And I think in the bigger scope outside this class, using seeds is probably the way to get around that. Yeah. And so just see, by the way, this would be analogous to taking a coin that you think is balanced, 50-50 head, tails, tossing it 10 times and counting how many times it lands on heads, right? And so where can I go from that? Let's say total equals the sum of those x values, the sum of vector x. Sum of x. Let's leave that, see what it says. Okay. And so of those 10 trials, 4 of the values were less than 10, right? And by the way,
Less than 10 or less than 0.5?
or less than 0.5, excuse me. Then the relative frequency, also known, right, that looks like it wanted it to be a command. Maybe I'll just say proportion is the total divided by n, right? And hopefully this is a 0.4, right? 0.4. And so if this was a balanced coin, we would have expected that to be 0.5, right? And what happens if I increase n? Okay, and so maybe n is 1,000, okay? And let's do the same thing. X is rand 1 comma n, close that, less than 0.5. Let's close that. Okay, does that look like I did it right? I'm terrible at this. Okay, and let's say again, total equals the sum of the entries in vector x. Okay, how many of them? Oh, 515. And the prop equals the total divided by n, or 0.515. And of course, this is just one simple example there, right? But we start to see anyways that for the larger n, the proportion, also known as a sample proportion, because this would be considered a random sample, is getting ever closer to that 0.5. Okay, granted that was just a single simulation, so it might not have been very convincing, but that's the idea of that, right? And in fact, if we like that, let's see if I can do this. And by the way, this particular activity thing that I'm working through, it is posted in Canvas. If you go to modules and you look under activities, what I'm doing here is right there. in years past, I've had everybody log into MATLAB, and we've kind of done it as a group, and that has worked with mixed results. So I thought I'd just try it this way this time. You know, so that's there. And also in the code, you see a way to make a loop. So in that loop, you can let n increase, right? And then you can do a graph of it, okay? In fact, I kind of want to do it if there's time. Let n be 1. Okay, this. That's not what we wanted. 10,000, sure. There. This creates a string of n's, a sequence of integers from, creates a sequence of integers, spelled wrong, 1 to 10,000 in steps of 4, steps of 5. Right. And we'll let I be the length. And so I will go 1, 6, 11, so forth and so on. Okay? Right. Again, I don't know if you want me to explain every single line. It's in MATLAB. Relative frequency builds a 0 vector. Okay, so a 0 matrix. Let's see, I got something going on here. Here's 0. Do I like that? I like that. Okay, I like that. That's going to create a matrix and pad it with zeros, which we can then put our results into, right? Then we can start a loop for I equal 1 to I, okay? This is the start of the loop. All right, let's let x equal random 1 comma n sub I. Let's see if we like that. We like that. Okay. Again, less than 0.5. Suppress that. Okay. So what's that's doing is doing that logical choice, less than 0.5 versus greater than 0.5 for each entry for that particular value of I. So we're first doing a sample of 1, and then a sample of 6, and then a sample of 11, and so forth and so on, up to a sample of 10,000, right? Yeah. Okay, and then let's let that proportion, the ith entry in that proportion, be equal to the sum of the x's, those are capitalized, divided by that particular sample size. Let's see if we like that. Don't want to make a mistake because I'll never fix it. Okay, and we'll go n. And let's just see, I'd like to kind of cut to the chase here. I didn't expect to spend quite this much time on this, but
Isn't that how it always goes with coding?
isn't it?
Always.
You know, and I was kind of thinking maybe I should write the code and then just open it, but then that kind of defeats the purpose of watching me sweat. And so let's just see what this does. Cross our fingers.
Yeah, that seems about right. at that level.
Does that seem
Oh,
about
there it
right?
goes.
There. Oh.
Look at that. Oh,
Okay, and I didn't try to index anything or anything, but what you notice here, as a couple things here, right? The number of trials is down here. The relative frequency is along here. You remember we were targeting that against 0.5. And to answer your question, are they equally likely or not? Well, they don't need to be, because that 0.5 could have been a 0.7 or it could have been a 0.9. You know what I mean? And so you notice a couple things here. You notice that it's bopping around all over the place, but it's bopping around that central line, right? The central line of 0.5, okay? Now, I do know that anytime I've talked about convergence of sequences, you know, going right to the definition of it, for any epsilon greater than 0, there must be some n value that contains it after that point. So you need to see this necking down. You notice also that while it might start out wildly oscillating, you know, you start to see it temper, right? Right? That's another key feature you want to see in this convergence. So this is intended to be a quick little demonstration of that law of large numbers, that the relative frequency for small n might not be very representative of the true probability, but as the number of trials increase, it gets closer and closer and closer. Does that make sense? You know? And so that notion of the law of large numbers is what justifies, is completely what justifies the notion of using simulation to estimate distributions or probabilities, right? Or failure rates or things like that, you know? So I say that let's just go back down here. So we say that it also not only does it work for an individual probability or proportion like that, like the probability of A versus not A, but you can also think about it in terms of whole distributions. Well, I said that RAND command, that RAND command, whoops, that happens every time. Have you noticed that in every classroom where there's a whole bunch of markers out there that teachers have left, they never work? That this RAND command randomly generates values between 0 and 1, right?
Can you expand that boundary?
You absolutely can.
Okay.
Yeah, it wouldn't be this command, it would be something like RND uniform, right? And so, if we were to look at, well, let's see, what do we think that thing would look like? Let's use a small n for now. Let's just say n is equal to 10, and x equals rand 1 comma n. Okay, and I'll suppress those for a second. And again, this is kind of in your. This is a little more what I'm asking us to do on this homework assignment, right? And so, I don't know, a hint, histogram, sure, let's just keep it nice and simple. Histogram of x, let's see what it does. Oh, I didn't like that at all. Okay. All's not lost, okay? By the way, how about if we go bins equal 10, right? And then I go histogram x comma bins. Let's see what we. Okay. Interesting. Okay, so you get a sense of that. There were 5 values between that were up around 0.9. That's weird. That's weird. Okay, what do you expect that distribution to look like? What's it going to look like as n increases? Right, because that was only a sample of size 10. Right, right. You know, let's see. What if I say n is equal to 1,000, right? And now I think I have to repeat all of these. X is random 1 to n. Close that since we don't want to repeat them. I think the bins are okay. The histogram. X comma bins. Let's see. So we increased the number of trials. Okay. What we did was we increased the number of entries in our vector, right? Because this is all vector based, right? And what does that do to things? Oh, okay. So you're starting to see. You saw the first one, and we all kind of shuddered, like, what on earth is that? What that was n was only 10, right? N is 1,000 here, okay? You're starting to see maybe what you're expecting to see, okay? And and by the way, let's do what I do on the 1, 2, 3, 1, 2, 3. Let's let n be equal to 1,000,000, which is kind of a standard simulation size I'm going to ask each of you to do in there, okay? And x equals rand 1 comma n, close it. We definitely want to suppress this one. Okay, let's go. Histogram x bins. Let's try this again, see what this looks like. Now we have a sample of it. Now we have generated 1,000,000 of these, right? And you see what I mean? You see how as the number of trials is increasing, it's getting us closer and closer and closer to what that true distribution might look like. And by the way, if it were randomly generating digits between 0 and 1, what do you expect this to look like? You expect it to just look like, you expect all of those columns to, in the long run, have the same height, don't you? Right? Okay? You start to see that property, okay? And another thing here, okay, is we want to be able to, I know I'm introducing a couple terms we haven't talked about, but we want to be able to use this to represent a probability distribution, okay? Now, a probability distribution has the property that across all the probabilities, quote unquote, sum to what? 1. The unity principle. Now, that quote unquote sum across all the possibilities, there's an uncountable number of possibilities between 0 and 1, right? So that notion, so as a probability function, that sum of the probabilities sum to 1 equates to the area under the curve is 1, right? So clearly the area under this curve is not 1 because we've got 10 times 10 to the 4 observations in each of those. We can normalize that, okay? And indeed, everything I ask us to do, I ask us to normalize it so we end up with something that, roughly speaking, is estimating a probability distribution. And histogram, let's see if I can do, X. Let's keep those same 10 bins, okay? By the way, more bins would show more refinement. Normalization in single quotes. That says it's gonna rescale it, or it's gonna rescale particularly the up and down. Which one is that? The vertical axis, so that an area is something you specify. okay? This happens to be a continuous random variable, okay? And so for a continuous random variable, we employ the unity principle with the command, and again, this is in the homework PDF for probability density function, right? And what you're gonna see is that the shape of that histogram is gonna remain the same. All that's gonna change is the indexing on the vertical axis so that the sum of the areas sum up to 1. Please.
And both of those are just built-in commands for MATLAB?
Yes.
That's nice.
Yeah. Oh no, it's super powerful. It's pretty amazing. I wish I knew it better, but you know. And now you see how it rescaled that vertical axis, right? So now, what's the area of the shaded? Well, it's approximately 1 times 1, approximately has an area, well, it doesn't approximately, exactly has an area of 1. You see what I mean? And so this might be what I write in your homework. Here is what would be a discrete estimate of the continuous random variable, okay? So what I ask you to do on homework number 2 is generate some of the 2 of these, column, like in the homework I say column x1 and x2. So you have 2 uniform distributions, okay? Both of them, and so you have these 2 uniform distributions. Where was that pen? One of these might work, okay? And you have x1. x1 is a vector, length 1 million, right? With random numbers in the, probably it's a open, but it should be closed. 0, 1 interval. Okay, looks like that. x2 is the same, right? Then the part that I'm going to stop just before doing, what I actually ask you to do is, what happens when you add 2 of these random variables together, right? If I say y is equal to x1 plus x2, right? Well, that's creating a vector of length 1 million with x1, 1 plus x1, 1, x1, 2 plus x2, 2, x1, 1 million plus x2, 1 million. Right? So y2 is also a vector of length 1 million, okay? Don't forget that since x1, each x1 value is between 0 and 1, each x2 value is a value between 0 and 1, each y value is a value between 0 and 2, right? So if we make a histogram of y, the sum of 2 uniform random variables, what does it look like? Right? Is it going to look like a rectangle, or is it going to look like something else? I don't know. That's what I ask you to do in this homework assignment, right? And I ask you to do it for first 2 of them, and then add 3 of them. W is x1 plus x2 plus x3, where each of those 3 is the same random 0, 1 random variable. And what will those new distributions look like, right? And so, and again, that's kind of getting to the heart of simulation, the heart of Monte Carlo simulation. We want to know what the sum of 2 uniforms look like, or I shouldn't be using terms we haven't defined yet, but this uniform distribution is this rectangular block. If I add 2 of them together, what does the resulting distribution look like? Now, of course, we could do some math, and we could actually mathematically prove it to ourselves, which I am kind of guessing no one in this room would want to do, right? Simulation is a way to kind of backdoor in to get a sense of what that distribution's really gonna look like. You know what I mean? And so, how does that feel? Does that seem like an okay conversation for this first one?
Yeah.
Give this a go. You know, I know it's our first time, and I know we have varying degrees of exposure to MATLAB. Let's find a way to make this work. Okay? Okay? Any questions, comments, concerns, compliments?
You did a great job.
Yeah, great job. Thank you. Thank you. Okay. Oh, look at that. That was the first 20 minutes of class. You want to take a little break? Let's take a 10-minute break, and I'll shut everything down, and then we'll talk about independence.